For this type of testing because its location was so remote that nearby communities would not be in danger, and of course the weather permitted year-round testing. Okay, fast forward a few years. It's now 1957, and the Navy was testing the Vanguard rocket to send the first satellite in space. They had sent up 2 of these rockets on suborbital test flights. But we're all in for a big shock on October 4, 1957, when the Russians beat us to the punch, launching Sputnik, the first man-made satellite into space. The race for space was now on, and soon the name Cape Canaveral would be one of the most well-known places on Earth. Soon after Sputnik was launched, NASA selected the first astronauts to participate in our manned spaceflight efforts, Project Mercury. And one of the main goals was to learn as much as possible about space, to help us to get ready to go to the moon. On May 5, 1961, Alan Shepard became the first American in space with the launch of the first Mercury flight called Freedom 7. Although his flight was suborbital and only took about 15 minutes, the U.S. had done it. We had put an American into space for the first time. In that same year, President Kennedy told the world that the U.S. would be striving to put humans on the moon and bring them back safely by the end of the 1960s. So with this new deadline, training and flights began getting fast and furious. After the Mercury missions were complete, Project Gemini was launched. Astronauts gained valuable information on docking in space while also performing the first American spacewalk. But with the last Gemini flight in 1966, all eyes turned to Apollo, and the moon was our next target. It's amazing, isn't it? In just under 10 years, we went from barely understanding how to get humans off this Earth to preparing to send them to the moon. So on July 20th, 1969, the nation's goal of putting humans on the moon was realized when Neil Armstrong and Buzz Aldrin landed at the Sea of Tranquility on the moon.
Tranquility Base here. The Eagle has landed.
This flight was followed with 6 other Apollo flights, with Apollo 17 becoming the last flight to the moon. NASA quickly closed the book on the moon missions, focusing their talents and technology on a new craft called the Space Shuttle. Now, many of you watching this have never known a time when humans weren't flying in space. A lot of us take that for granted. But let me tell you something, it's not easy to prepare everything you gotta do to get up to space. All right, so are you ready to go on a tour? Let's roll and check out some of the facilities here at Kennedy and meet some of the hardworking people that are making these spacecraft fly. The VAB is where the space shuttle gets assembled for spaceflight. This is how it works. First, the solid rocket boosters are mated together and attached to the giant external fuel tank. Then the orbiter gets towed and raised to a vertical position with overhead cranes. It's attached to the other components and is ready to go. Well, almost ready to go. So how to get the orbiter out of this building and onto the launch pad? Well, with one of the baddest moving trucks you've ever seen. Around here, they just call it the crawler. Tell me about the crawler.
Well, Johnny, the crawler was built about 1965, and it was basically the main transport to take the Apollo vehicle from the vehicle assembly building out to the pad.
This thing is huge.
It's 130 feet long, about 115 feet wide.
And what's max weight on this thing?
Well, let's see. The crawler, it's about 6.5 million pounds. Pretty heavy. So it stays on the ground, no problem.
Yeah,
you know? But the crawler carries, right now it's carrying about 13 million pounds.
13 million pounds.
Yeah, so you got a total weight of crawler and vehicle of about 18 million some pounds.
Oh my goodness.
Rolling down the road.
I'm going to assume this thing doesn't go very fast.
It's not real super fast. We like to keep it probably around 1 mile an hour. Now its design speed when it was first designed was almost a speed of 2. But actually it is fast when you're on the crawler, I mean because of the mass that it's moving.
So you fill a tank up. I'm just going to ask you, if you fill up the tank, I mean, you know, what can you get per gallon?
Well, it's about 38 feet per gallon.
38 feet per gallon.
Oh yeah, yeah. And we actually have 2 tanks on the crawler. Each are 2,500 gallons apiece.
Oh my goodness.
Yeah. So it'll last a couple of operations.
Tell me, what does the crawler do?
Well, the crawler, the basic task of the crawler is to pick up the mobile launch platform. The mobile launch platform, of course, has the vehicle stack on it.
Sure.
And it moves it from the assembly building and it moves it out to the pad. And then sets it down and then moves back away from it. And then once the vehicle launches, it goes and picks up that mobile launch platform and brings it back to the vehicle assembly building for another stack.
Is there only one crawler?
No, there's actually 2.
Oh, there?
Yeah, NASA had 2 of them built back for the Apollo program.
All right, so we know what kind of mileage this huge thing gets. How's it powered?
Well, you know, funny you should ask that. Why don't we just go up here and we'll check it out?
Let's go.
Yeah, walk back into history.
Oh, look at this.
These engines here, those are the same engines that have been on here since '65.
Since 1965.
This is what powers the crawler here. There's actually two of these. There's one here,
Okay.
one on the other side,
Okay.
and each one of these powers two 1,000 kilowatt DC generators.
Really?
Kind of works like a diesel electric locomotive.
Sure. Let me ask you, so how do you move this thing? How do you drive it?
Well, come on, I'll show you.
Sure.
We'll walk right up here. Okay, Johnny, come on. Let's come in this cab right here.
Okay. Oh, cool.
This is the operator's cab.
Wait a minute, wait. That's the steering wheel?
Yeah, it's not your typical steering wheel.
For such a big rig, my God.
For probably one of the largest vehicles, this is quite a small steering wheel. The steering itself is, of course, it's all electronic.
Yes.
And what's happening with this wheel is when you're turning it, it's sending a signal back to what we call our PLC, which is Programmable Logic Controller.
Okay.
And it takes that signal, sends another one out to some hydraulic pumps that in turn move these large cylinders out here. And
Cool.
the cylinders themselves move the trucks back and forth.
Sure.
And of course it steers itself down the crawlerway as to, you know, depending on what kind of degree you put in.
Is that how you control the speed?
Exactly. This is just like a foot pedal, you know, a speed pedal in the car. What you're doing here is you just increase the spot control, and it takes those. When we looked at those generators back there, it excites those fields.
Yes.
And by exciting those fields, we can adjust the speed of these propel motors down.
Huh.
And then along with the gas pedal, you know, you got a transmission. It's just like a car, forward, neutral, reverse. The other thing that the crawler operators are always worried about is its height, because one of the basic operations of the crawler is moving the mobile launch platform out to a set of columns, setting those down and moving out from under it. So he's always aware of what his height is, and he does it here by this average height here.
It's been a pleasure. It's a lot of fun. Thank you so much for bringing us around today.
We enjoyed it, Johnny. We're glad to have people come out and take a look at our machine.
Definitely. This was a lot of fun. You're watching NASA 360. We'll be right back.
Wow, that crawler, it's huge. To give you a better idea of just how big that thing really is, listen to this. Those tracks that they use each have 57 shoes, and those shoes weigh nearly 2,000 pounds each. All right, let's switch gears a little. You may have heard of something called the thermal protection system on the shuttle. You know all those black tiles along the bottom? You may also know that they help shield the craft from the 3,000-degree re-entry heat when it comes back into the Earth's atmosphere. But do you know what they're made of? Well, it's a pretty cool story. Johnny is over at the Thermal Protection System facility to see how the process works.
Okay, so we're here at the Thermal Protection System facilities with Martin Wilson. How are you?
I'm doing great.
Good to see you.
You too.
And this is where tiles begin life, right?
This is the part of the process where tiles begin. You know, this object right here is called a tile production unit.
Okay.
Weighs about 3 pounds. It's a very low density material, rigidized fibrous ceramic, capable of withstanding around about 2,400 degrees, over 3,000 for very short periods of time.
Sure.
And we make these billets, as we call them in here. We start off with several different types of ceramic fiber that are all pre-kitted and pre-weighed.
Yes.
These materials are put into this blender that we have over here with about 25 gallons of water and various chemical additives, ammonium hydroxide, silicon carbide, other surfactants and what have you. We put them in this machine and basically turn it on, and it blends the fiber for around about 12 minutes.
Okay.
And after the blending process is done, we go ahead and we put it in this casting tower over on the other side of the room. This device here is called a casting tower, and it's really simply a hydraulic press. We have around about 25 gallons of the prepared slurry, which is the chopped fiber, water, surfactant, and the other additives.
Sure.
And we now go through the process of loading it into the press. And despite many years of high-tech methods of getting the slurry from the bucket to the tower, this is how we do it. It actually takes about 25 gallons of water to produce one block. And actually for the CEV, for the Orion, we're using this. That's actually what this is for. Because these tiles are very light.
Right.
Extremely resistant to micrometeorites, and because of the trajectory of the new vehicle, it's going to see some pretty high temperatures, but for fairly short periods of time. And now they start this gradual dewatering process, which actually takes a little while to do. At this stage of the process, the billet's been pressed. The next step is to actually extrude the billet out of the tower. At that point, it'll be taken to the other end of the building, dried for 16 hours at 250 degrees, and then ultimately fired in a kiln at 2,450 for several hours, and that will give you the block that I showed you to start off with.
So we are in a new section of the building. Why don't you tell us where we are and what do you do here?
Well, this is the machine shop, and this is where the actual base tiles are machined out of the billets of material that we produced down at the other end of the building. There's several different ways we can do that, but primarily all of the tiles are machined using diamond-coated tool steel cutters, either on a manual machine, which is called a tracer mill. The majority of the tiles we actually produce on these machines back here. This is a 5-axis numerically controlled mill. They use these type of tools. These are diamond tool steel cutters. This machine is highly automated. The program originates back in the numerical design area.
Okay.
The entire process takes about 20 minutes.
Sure.
In the beginning, we'll start off taking a series of rough cuts just to take the bulk of the material away, and then there's a series of smaller and finer tools that will come in and start to take those surfaces away.
So once they come out of the machine shop?
Yes, the next step of the process is to actually apply a series of ceramic coatings. The materials themselves, at this point, do not have a lot of strength. So we put a coating on. It's either a black or a white coating, depending on the emittance properties required of the tile. And it's put on in several layers. We make the coatings in here. They're basically very finely divided ceramic powders, either in alcohol or water, with various thickening agents and emittants and pigments. They're all sprayed by hand. The coating goes on in basically a 3-step process. But again, it's one of those processes that is a very exacting. A lot of weights and measures to make sure the coating is of the exact correct thickness. This is the step that follows the application of the coating.
Okay.
That we just saw. The coating has been applied and dried for several hours just at room temperature.
Sure.
But for the coating to consolidate or sinter, it has to be heated at 2,200 degrees for 90 minutes.
Okay.
That's what we do in these kilns. And we have a tile in here that's been undergoing that sintering process, and we can go ahead and take it out. The tile's at 2,200 degrees. And you'll be able to see how the black coating starts to cool down very, very rapidly.
Yeah.
Now this is just raw, uncoated material.
Sure. Look at them, they're glowing inside.
But those you can actually go ahead and...
These you can pick up?
Yeah.
These?
Yeah, you can just go ahead and grab them.
Are you kidding me? Am I doing it right?
Yep. Just pick them up by the corners.
I'm so
and
afraid to. What's that? I'm afraid to.
as long as you just handle them only with the lightest of pressure,
At the lightest of pressure.
you can go ahead and pick them up.
This is so cool. It's 2,000 degrees.
Yep, it's 2,000 degrees. It's cooled off fairly quickly on the corners, and that's the reason you're able to pick it up. It's still 2,200 degrees in the middle. It will burn you if you're not too careful with it.
Of course.
But it is silica, it's very low density, and has a relatively low heat capacity, which is the only reason you're actually able to do that.
So, tell me, how does the shuttle tile work?
Well, in its simplest terms, a tile like this one here is really just a very, very lightweight, but a super insulator.
Okay.
I mean, you can put heat to one side of it, and eventually the backside of the tile will get hot. But for any type of re-entry vehicle, you know exactly what re-entry consists of. So you know approximately what the heat loads are going to be, so then it's just a question of designing the tile to be of the correct thickness. And I can actually take this tile and heat it up with a blowtorch, and you can see quite rapidly the surface will get up to about a little over 2,000 degrees with just this propane torch.
Okay.
But the actual heat is soaking through the tile very, very slowly. I could stand here for probably around about 20 minutes.
Yes.
Before the back of the tile becomes uncomfortably hot and I'd have to put it down.
Really? It's not hot now? On the other side?
No, it's not hot at all. I've got my finger right on the back side of it and I can't feel anything. It's probably going to take about 7 or 8 minutes before it starts to warm up. So yes, you can put your finger on the back of it.
Yeah,
it's just nothing.
Nothing.
And basically that's how most of these ceramic insulating strategies work. Just very, very lightweight. They delay that heat pulse.
Yes.
And can be used for any re-entry vehicle, be it an Earth re-entry vehicle or a one entering Mars or any other planet.